Also, we will share the feedback form at the end of the session. Please fill the before leaving it. The second day of the first speaker is Dr. Mangalaraja Ramalinga Viswanathan. Dr. Mangalaraja sir is working as a full professor in the Department of Materials Engineering, University of Concepcion and at Concepcion, Chile. He worked as a director of international relationship at the center at the University of Concepcion for the year of 2018 and 2019. He served as a director of the Department of Materials Engineering at the University of Concepcion for 6 years from 2010 to 2016. He also served as president of the Chilean Meteorological and Material Society for the period from 2015 to 2017. He is a life member of Indian Ceramic Society and a fellow of Indian Institute of Ceramic. Also, he was a member of the Mineral Metals and Material Society and Singapore Material Research Society during 2017 to 2018. He was a member of American and Japanese Ceramic Society during 2010 to 2012. Dr. Mangalaraja received a PhD in technology from Anna University, Chennai. He has postdoctoral experience from AIST, Nagoya, Japan, Luleå University of Technology, Luleå, Sweden, and Anna University, Chennai, India. His primary research interests are focused in the area of nanotechnology-driven advanced ceramic and micro nanostructure property relationship of the functional and structural ceramic and metallic composite materials. He is the author of or co-author of over 190 reviewed international journals publication and 12 book chapters and 3 patent, one of the editor in the book, and more than 150 research presentations, invited talk in several international conferences. Dr. Mangalaraja sir, under the guidance of, there are 8 PhDs have been awarded and 15 post of PhDs have completed their postdoctoral research in the field of energy and environment. Further, he has participated as a responsible and co-investigator of 35 research projects funded by ANIT National Agency for Research Development, Government of Chile. He had been acted as a member in the expert committee of FOND ECYD ANID for 2 times the area of material science and engineering, and now extending his expertise as a reviewer of various projects in the area of material science and engineering. Dr. Mangalaraja sir.
Yes, thank you. Thank you, Dr. Murugadas, and thank you. It's my very pleasure and good morning to all the spectators and viewers of my presentation. It's a pleasure for me to present this seminar, and I thank Dr. Murugadas for the great opportunity and the Satyabama Institute and also other colleagues. Anyway, it's my great pleasure. Anyway, I'm at the midnight here in the Chile, the other part of the world. So you have time 10 o'clock, but I have 12:30 exactly. Well, today the topic of my talk is just I want to focus on the challenges and strategies in the processing of advanced materials for energy applications. When we talk about advanced material, you can take either metals, alloys, composite, or polymers, any kind of materials. Normally, these kind of strategies and challenges are suitable for many material, any composite. But particularly in my case, I have much focused. We have much focused on the ceramic material, advanced ceramic material. Normally, advanced ceramic material in the sense, normally people think is whenever we think about advanced materials, we normally think about nanostructure materials. So today, the now current world is focused on the nanostructure. Even in the future, we don't know what kind of materials we will exit. And so, also the current trend is to focus on the energy and environment. And particularly in this case talk, I focus little on the energy applications. this picture, you can see where I am from, and that the Chile. This is our campus, um, which is located in this south region of Chile. You can see the map on the right hand side that total energy production in the worldwide. It is on the million tons oil. It is noted in the different countries in the right hand side. Also, the below right hand side below, you can see the energy total energy consumption worldwide. How which country is consuming how much energy. So you can see that in the main production, the number one, number two, or in the production in China and the United States. In other case, in consumption, also China and the United States are in the leading uh, positions. So based on this talk, like energy topic, just I want to give some introduction about the trends, current trends. Normally, in this talk, just I have focused that what we are doing, and that based on the current trends, and the importance of the miniaturization, because we are talking about the nano structured materials and nano materials, also the advanced materials. And so, what is the part of importance of miniaturization when we talk about the nanostructured materials and the research lines? But normally, when we talk about the research, that we have to focus from science to applications. Nowadays, without applications, if you any science in normally the art countries focusing towards application point of view, and even the projects and the research projects, all the government worldwide, they are interested in the technology-based projects, because they think that the more technologies, more patents are needed for worldwide. So in that way, we have to focus normally our basic research towards applications. So also I will give some details of our results, the research results, in particularly in energy and conclusions. Okay, well, here I have focused that, as I mentioned, that nanostructured materials in two parts, like energy and environment. Energy point of view, we are doing some works on the solid oxide fuel cells, and more recently, we also have started solid oxide fuel cells and these reversible solid oxide fuel cells also, and some works on solar cells and optoelectronic devices and magnetic refrigeration for green energy, green refrigeration. And in the environmental side, we are focusing some special um, applications for sunscreen cream materials. Of course, we developed the cream materials for real life applications, and some works on the photocatalysis, and some materials for wastewater treatment, like filters. So in this case of energy, and that as I mentioned about solid oxide fuel cells, we have developed a prototype solid oxide fuel cells, which is supported on a mini tubular nickel and gadolinium doped stereo anode as an industrially viable energy source. So this fuel cells, normally you know that fuel cells, what is called fuel cells? Fuel cells are devices that transform the energy, chemical energy of fuels directly into electrical energy. So this fuel cells what we are focusing, that solid oxide fuel cells called SOFC. It has all the materials of components of ceramic materials, like ceramic electrolyte and the electrodes. Which are operating the fuel cells operating at high temperatures around some 600 to 1000 degree. Also, this electrolyte, fuel cells have high efficiency. So three components are there in anode, electrolyte, and cathode. So what is the requirement of this SOFC setup? The anode and cathode should be a mixed conductor, like electronic and ionic conductor. Also, it should be like a porous structure. In case of electrolyte, I'm sorry, it is in Spanish. Electrolyte, it has to be an ionic conductor and the electronic insulations, and also as well as this material, electrolyte material should be high dense, should be 100% dense materials, because it needs to conduct a ionic conductor. You have to get the best ionic conductors. So you can see, the based on this technology, based on the power production, you can apply this kind of fuel cells to different energy sources. I mean, the applications, like it depends upon the energy, how much we are producing, from 1 watt to 1 megawatt. 1 megawatt. So there are different, even you can see there are some fuel cell vehicles, adaptive materials, and some portable applications also available, and nowadays is currently available in the market. So what is the strategies and challenges to process these kind of materials? In this kind of material, in the sense, we have to give a better performance of the solid oxide fuel cells. When we talk about the efficiency performance, we obviously we have to focus on the processing of materials. Generally, when we think about overall strategies to improve this kind of fuel cells, we have to think about the cell support, what kind of support it has to have, and what kind of geometry it has to have, and what kind of material it should be fabricated and be fabricated, and that we have to analyze. So cell support, geometry and materials. Material in the sense, you can take all materials. Here in this case, anode, electrolyte, cathode, and also sometimes when we connect, integrate many cells, you also need interconnect. So we, in this case, we have to think about new materials for anode, new materials for electrolyte, new materials for cathode, and new materials for interconnect. To Because these kind of cells are operating at very high temperature. Nowadays, the trend is to lower the operating temperature at the same time without losing the efficiency. So we need to we need to focus new materials which can give high efficiency, as well as can operate at low temperature. Also the geometry, what kind of geometry can be give more support and more important in the case of both the electrical and electronic properties, as well as the mechanical properties, and which kind of support can give more flexibility and more thermal stability. So all the cases, we are thinking about all the points of view, we got to think when we process. And process in the sense means from the powders to the product, powders to the product. From the powder, we got to fabricate, and we got to obtain the product. So every step we have to think, and we have to calculate, we have to arrange our methodology of research in each point, in each step, to obtain a very good kind of materials, in the sense high performance materials, so that we can improve the efficiency of the solid oxide fuel cells. So when we think about initially the cell support, traditionally the people were using the electrolyte support fuel cells. This electrolyte support fuel cells means on the traditional electrolyte was used like in the beginning. And from the beginning, they are using this. So stabilized zirconia, which is a very high stability ceramic used traditionally. Nowadays, to operate, to reduce the operating temperature, people are focusing new material kind of cerium oxide based materials, and now recently lanthanum ferroscrete material also recently is coming. Um, so every decades there is a development on the materials, new search on the materials, because it's a aim to improve the efficiency. So initially it was like electrolyte support. Now we are focusing the anode support. When we think about electrolyte support here, in the case of electrolyte, it was to be very thin, so that it can, the conductivity can increase. When we have thick electrolyte, it has need more time to travel, and needs more time to travel from one side to another side, anode to cathode. So it takes time. And when we think thin electrolyte, so it can it can have a very fast movement of ionic conduction. So that we thought about anode supported. When we have anode supported, then we have to think about what kind of design, it has to have. So by decreasing the electrolyte thickness, at the same time, we have to maintain the mechanical properties. So mechanical properties, and obviously we are maintaining, some other element has to have a big support. So at the same time, we have to maintain the mechanical property. So this reducing the electrolyte thickness reduces the polarization effect. So with this concept, and we choose a tubeless kind of mini fuel cells. Why tubular kind? Because the other designs like a flat sheet and zigzag kind of things are not that much mechanically resistible. So we choose the tubular kind of cells which can give more mechanical support, mechanical strength. So it will increase the power density and give better mechanical performance and simplicity in the sealing of the fuel cells. So based on this idea, we found that gadolinium doped ceria materials can give better ionic conductivity, as well as it can reduce the operating temperature. So by this way, when reducing the temperature, you can see the wide field of applications, mobile applications, then to put up applications, and then decrease the start time and reduce the material cost. So you can see the general objective that manufacturing mini tubular. Manufacturing in the sense, you have, as I said, that from the precursor, starting precursor to product. So you from basic science to applications. So manufacturing from powder processing, and then fabrication, and then sintering, and then you can have the final product of the fuel cells. So so in this case, we choose the mini tubular. Why? Because mini tubular, when we integrate mini tubular, many kind of mini tubular, you can have the integrated energy. That, for example, we put one cell giving 1 watt, for example. If we integrate some 100 cells, it has to give minimum 100 watts. But sometimes when we integrate many this similar 100, maybe it can give 200 watts. That's the reason. So you can see the design of geometry of design of the solar cells also. You can see before it was one like a cubic, but nowadays you see the designs now. Many tubes set with like kind of series kind of cubic nature. You can see in the solar cells. The same kind of adaptation, same kind of adaptations that we have think that when we integrate mini tubes stacked one by one, like in the either in the cubic form or in the rectangular form, but we have to increase the number of stacks so that we can integrate the energy. So based on that, we we started to fabricate mini tube based anode based tubes. So in this case, initially we have to produce anodes, then we have to give the electrolyte coating, and then over electrolyte coating we have to give the cathode coating. Then we have to stacking the start that stacking of mini tubes. In our case, we have stacked some 9 cells, 9 mini tubes in the sense I'm talking about the micro tubes, and maybe it's outer diameter, I can say that it's 1 millimeter, but in the, you can see, if you see the thickness of the tube, maybe it's around microns, 800 to some 1,000 microns, 1,000 microns. I will see the later. I will see so the micrographs of these tubes fabricated. So these kind of tips. So as I mentioned that from the starting powder. So there are many methods available, but simple methods that we have to adopt. In our case, we started to synthesize in the rapid synthesis process called combustion synthesis. Also, we have adapted the precipitation technique. But even in this, now you have to think the powder characteristics. Normally, when you have good fabrication materials, you need spherical particles. But in kind of precipitation and other advanced all the chemical methods, it is easy to fabricate a spherical kind of powders. Also, you can modify the surface of the particles. So it is not a big task nowadays. So, but still we have focused rapid synthesis of making fine particles by through combustion methods. In this way, we adopted this combustion method for synthesizing three materials like anode, electrolyte, and cathode. So anode, that now that what kind of materials we choose: nickel oxide and gadolinium doped ceria composite. And so this is in the 65% of nickel oxide and 35% of gadolinium doped ceria. It's like as I mentioned earlier, it has to be have electronic and ionic mixed conductor. Also it should be porous. So I will tell you how it was fabricated. So it's a simple process that processing of powders that finally we get the powders. These powders, of course, nano-sized powders, and of course, we can have a spherical shape. When we have this kind of rapid synthesis, normally it is possible to obtain different morphology, irregular morphology. But we can add some surface controlling agent to have the spherical nature of the powders. So these powders, after preparing these powders, we have to start preparing the paste. So this, because we have to fabricate the tube, so we have to prepare the paste. So for that paste, we need to add different material, for example, different binders, and to make a pasty kind of nature, so that it is easy to extrude the powders. So how much amount of liquid phase was present, how amount of solid phase was present in the component, you can see about 27% of liquid phase and 73% of solid phase was used to prepare the paste. Of course, we use octanol and dimethyl formamide, and these are the composition that we have chosen to prepare the paste. Why I'm just stressing this paste? Because you see, maybe you can see the steps are very simple, but each and every steps we have to have an idea of finding innovative kind of thinking. So you can see them. You can sometimes with unknowingly you can get some good results. For example, when we traveled working this paste, just we left the space in the atmosphere for some time. It didn't lose the characteristics. It means that it didn't lose the viscosity and its originality. For example, normally when you leave the atmosphere, it has to dry first after some time. But the paste that what we prepared, nearly 3 months, it never it did not lose any characteristics of like its viscosity and nature and the humidity of this paste. So that this paste, you can see here how we mix this paste and how much the percentage and how we extruded the paste. This paste we have filed the patent. So because of it didn't lose its original characteristics for nearly 3 months. So we have filed the patent. This is unexpectedly we got this result. So we don't know what kind of result we get during the investigation. So immediately that we thought that okay, we can analyze the pest, how long it will have its own characteristics. So we tested and we wait nearly 3 months, and the 3 months till 3 months it didn't lose. So we filed the patent, and that patent it's now we have applied for the international patent. Initially we applied for the national patent, and then now we have applied for, and that was approved, and again the next step we applied the international patent. So with this using this paste, we started fabricating the tubes. The tubes, as I mentioned here, you see, with after sintering, you can see it has to give ceramic nature. Before sintering, green tubes, how it's giving its originality, and after sintering, how it's of course before sintering it is a green tube. Green tube in the sense I'm saying as fabricated. It has polymeric content and other material present. So after sintering, obviously all the polymeric content will evaporate. So it has to have the ceramic nature. What is ceramic nature? Because we have selected oxide. So oxide composite. So it has to give ceramic nature in the sense it has to be a fragile nature. So it has to obey the Cook's law. So when increasing the force, the deformation starts. At one moment, it has to fail without any plastic deformation. So, but before sintering, you can see there was a plastic deformation exist in the tube in the green tubes. So you can see here that green tubes are fabricated, not green tube in the sense you don't think about color. Green tube means as fabricated. And then after sintering, you can see that green color, pale green color. And after reduction, you can see, and why we are reduction? Because we need, for anode material, we need cermet. Cermet means ceramic metal composites. So we reduce only the nickel oxide and to create porosity, microporosity. Obviously, when we fabricate tubes, also we evaporating the polymers, also you get macro pores. So both micro and macro pores present in the tubes. These tubes acts as an anode for our fuel cells fabricator. After this fabrication of these anode tubes, fabrication and sintering and reduction of these fabricated tubes, we started coating electrolyte powder. Of course, for the electrolyte powders also, we adapted the combustion synthesis. So we started in many kind of methods are available in the such that methods for coating, but we have to think as a homemade coating. Whenever we need for a different approach, it's a possibility of inventing new ideas. So brush painting that we thought initially. Then later we made home kind brush painting, some kind of brush and spray painting, spray kind of painting. So for that we need to prepare a slurry kind of material. Before for fabrication we prepared a paste, but now we need slurry. Slurry means a liquid kind of material to spray and to like is paint spray coating of electrolyte over as the anode, over the sintered anode. So for that we need electrolyte also. We have to prepare like a slurry. For the slurry also we need to formulate the composition, and you can see the composition on the left hand side, that how much the percentage of each content of the material. So after that we coated the electrolyte. That coating electrolyte, as I mentioned in the initially, that it needs to have a very thin coating, but at the same time we need to have a high dense coating. So it's around some 80 to 60 to 18 nanometer, sorry, micrometer. So for that we got to have carefully, we have to adjust the composition of the slurry. We need trial, we could had many trial, and finally we achieved a green, high dense as well as very thin coating by in optimizing the composition of the slurry. So that composition adjustment as well as the homemade spray. So this is the kind of you can innovate new this spray coating also. We have filed a patent, national patent, but that is still under processing. So this coating we have achieved nearly 100% density. 100% density means without minimum porosity that we have achieved in the spray coating, in the spray coating, homemade spray coating. You can see the right hand side, you can see the anode tip in the black color, and over that in the white color coating, you can see the microstructure, how it is dense, the grains arranged over the porous microstructure of the anode. You can see. So with many trials, after that, finally we achieved a high dense electrolyte coating, and that was sintered at 1200 degrees centigrade. That both sintering together, anode sintering, the later over the anode electrolyte coating and sintering together, and then now we need a cathode coating. Cathode coating in the sense we need, obviously we need cathode powder. For cathode powder also we prepare the composition based lanthanum transient called ferrite and cadmium doped composite powders we prepare, and that powder also we use the similar coating technique and similar adaptation of formulation of slurry, and that over that we over the electrolyte we coated the cathode. You can see the right hand side how much the length of the tube is 5 centimeter. But if you see the cross section of the tube, you can see it's around 4 millimeter, and in the thickness you can see maximum 1000 microns. 1000 microns. In the majority, you can see the anode tube around 800 to 900 microns. So rest 100 to 120 microns has to have an anode, electrolyte and cathode. So this is the cross section. So one the thickness is around 1000 microns total. You can take total microns. That was easily fabricated by the technique that what the paste that we have formulated. These cells, after sintering, after coating of all together, after sintering, anode, electrolyte, cathode, finally we sintered. we sintered at 2200 because here you have to have three sintering steps, not one sintering. But when we have many sintering steps, normally the material lose its original properties, means lose its mechanical property. But we have to maintain the mechanical property, and at the same time, we have to control the shrinkage, every steps that we have to control. So for that we have to have different studies, basic studies we have to have. And normally when we have this kind of studies, immediately you can synthesize the powder, fabricate, and you cannot have, but you have to study the powder properties, and then you have to study the paste formulation, and you have to study the slurry formulation, and then you have to study the overall shrinkage of the materials. So each powders you have to fabricate, and you have to sinter like a pellet, and with this pellet you have to study the shrinkage, mechanical property, conductivity, both electrical and ionic conductivity. So overall these results, based on this optimization, we have to take the steps of following the powder synthesis, fabrication, and sintering of these fuel cells. So these fuel cells, so finally we tested, and it gave nearly 0.6 watt per centimeter cube at 600 degree. And then later we stacked the cells, and these cells, after stacking, you can have, obviously, in our case, maximum we reached 0.8 to 1 milliwatt. When we stacked the cell, if, for example, in case of 4 cells, it has to have 4 watts. But in our case, we used the converter. So converter, in the sense, converter may be some, it has opportunity to give multiple the energy. So in our case, it gave more than 4 if we stack 4 cells. So more than 4. So we stacked 10, then it gave 15 watt. So it's kind of using the technology, because not only material scientist people are working, can work only. Also, we have to get the knowledge from the electrical electronics people, so that it is we can have a good idea of making the final performance. So normally when we work in the team, like a multidisciplinary team or interdisciplinary team, that it is possible to have a very good results. So whenever you have a doubt that you have to stick with, no need to stick only with the material science or materials engineering. Sometimes when we collaborate with other discipline people, it's a possibility of increasing the outputs, increasing our results performance, and it's an easy way to obtain good results. So you see the microstructure of the tube. You see how much porous the anode, and how much dense the electrolyte, and how much porous the cathode. So that after making this stacking, we also think about series mode and also parallel mode. So with this integration, somewhat we tested, and it really gives a good result when we use the converters to integrate the efficiency, as well as not only integration, it soon add more outputs when we use the conductors. So we designed some new design for the stacks. You see. So these kind of cells, based on the output energy, you see, from mobile application to different energy efficiency, Actually, our focus is to use in the military purpose, to use in the drones, used in the military, maybe at least for 1 hour to work. We are on the way to reach that goal. Hopefully it will reach. During this stage of working on solid oxide fuel cells, the trend in the world trend is changed, of course. New energy devices like called when we are working on solid oxide fuel cell, it came solid oxide electrolyte cells. It means reversible solid oxide fuel cells. So that kind of reversible solid oxide fuel cells, electrolyte cells is at based solar energy. So without using any fossil fuel cells, and zero no emission of carbon dioxide. Now its trend is changed. So now we have switched parallelly. We have switched to solid oxide electrolyte cells too. For that, full and full ceramic based electrolyte cells, perovskite materials that we have started in our new projects. So it's a kind of when we lose the time, when we work on the time in the you see the research community all around the world is giving new techniques and adaptation of technology. So finally, the conclusion, it's only the conclusion of fuel cells, not the conclusion of the talk. And so it was possible to manufacture the solid oxide, mini tubular solid oxide fuel cell stacked with the power generation of single cell between 0.5 to 0.1 watt and centimeters cube. At maximum, we reached in some cells 0.8. And we also formulate the patent, and we also formulate the slurry as a patent, both paste and slurry formulation. Only the slurry formulation of electrolyte, not the cathode. And we are on the way to, as I mentioned, that generation of 100 watt with the medium power applications like using in the drones. So it's a one result, one project that we are still working on the development, and at the same time, as I mentioned, that we are also working on the graphene MaxSync based materials. Graphene means without, you see the layer structure materials nowadays in the graphene, more than graphene, you can see the max phase and MaxSync materials. When we are working max materials, immediately came a new kind of material, MaxSync, to eliminate the A element. So we started parallelly and working on the graphene, and of course, when we worked in the graphenes, during this work, we started fabricating the max phase materials. Why the max phase materials? Max phase material, of course, already established max phases are existed here, like titanium silicon carbide, titanium aluminum nitride. But our aim was to focus this max phase to improve the copper material. Chile is main exporter of copper. So here we have a lot of mines, copper mines in Chile. So obviously we have to focus research process based on our natural resources, so that we started working on the development of copper materials, copper material. So we started, what is the advantage, what is the disadvantage of this copper that we focus. So the main disadvantage of copper is it's low mechanical strength. So obviously copper is a high conductive material, but it has some drawbacks like mechanical strength. So we focus on improving the mechanical strength. At the same time, not compromising its original property called the conductivity. So when we create composite, normally it's like a rule of mixture, but you see the trend is not nowadays rule of mixture. Trend sometimes it give more And that's the reason that I mentioned the nanostructured material. Maybe nanostructure in the sense you can take in the sense of particles shape, or fiber, or you can take flakes, or you can take two-dimensional, other kind of two-dimensional materials like graphene, maxine, or max space materials. So that we incorporated the max materials in the copper matrix. So we unexpectedly we improved the much improved the mechanical properties, especially in the hardness of the materials are very much improved. And you can see that a distribution of how the uniformly distribution of the copper Qmax, that copper max composites with improved mechanical. That too you fabricated in the hot press. With the different sintering temperature, 500, 600, and 700. So you can have, when you have a homogeneous distribution of this max phase, obviously the max phase helping the improving the mechanical strength, as well as maintaining the kinetic conductivity of the materials. When we working on this material, immediately we find that maxine kind of materials, that maxine kind of material from the max to eliminating the A element, which is called the A element present. For example, just to remove the A element, you can have the maxine layers. That maxine two-dimensional layers, it gives much more better than the max. It can give more electrical conductivity. So now we are focusing to maxine, copper maxine material-based materials to have a high performance of the electrode. Electrode in the sense copper electrode used in the using in the electrical contacts and welding, resistance welding applications. Further, I also would like to add some techniques of sintering, because there are 3, 4, 5 groups, I think, 4, 5 groups working all around the world that is fast sintering techniques. Well, we have a different sintering techniques, conventional hot pressing, spot plasma sintering, and flash sintering. This flash sintering is a very fast technique. Normally, when we use for conventional sintering, you see it takes normally 1 day. 1 day, increasing the temperature and maintaining the temperature, and then cooling the temperature, and then you have to take out the final product. But in this fast plasma sintering, after the hot press came, hot press maybe I can say that 3 or 4 hours, and then plasma sintering came, maybe spot plasma sintering maybe around 10 to 30 minutes. But in flash sintering, you can see in few seconds, you can sinter the samples. But it's not yet commercialized, but it is still under developing. But you see, within few seconds, you can reach 1,500, more than 1,500. It depends upon, of course, it depends upon the materials, nature, material conductivity. So this plasma, flash sintering is now under investigation, and this technique seeks reduce the sinter time and temperature associated with the ceramic materials. With applying different electric field, you can really get good nanostructured materials, because getting nanostructured materials in the few seconds is very, very important, and because sometimes rabbit sintering can increase the abnormal grain growth. But in our case, you see with flash sintering at 850 degrees centigrade, just 5 seconds, you come and compare with the traditional sintering for 1,400 for one day. It is 5 seconds in 850. You can see the here you can see the how the flash sintering occurs. You can see the um, grain arrangement and grain density, how the sinter intensity occurred with nanograins. So it is possible in few seconds you can have of course it also needs optimization with different applying electric field and different current density, and we have to optimize, of course, with the different times we have to. So these kind of techniques normally give very good nanostructure materials. So by the way, by adapting new techniques, we can also improve the material properties, as well as we can have the innovative results. With this, I just want to conclude my talk. Maybe some results are missing. I think that because I just remove some applications of environmental focus, and just I focus only on the energy side. So with this I concluded. Finally I just want to give some research opportunities in the Latin America, especially in Chile. For example, there are many opportunities. And currently, when I remember when I came here, only few Indian people were working in our university. Nowadays I can see many researchers, especially for postdoctoral researchers, having their opportunity to come not only in my university, all around Chile, and there are many people, Indian people are coming. So there is a postdoctoral fellowships available, like a Fondisit, ANID Fondisit, ANID, Agency National Investigation and Development, and Fondisit called ANID Fondisit postdoctoral fellowships available. Maybe in the this month, maybe in the during August, maybe you can see the call for. And this is a great opportunity, and it is not only a great opportunity, this is also good fellowship. Also, the working culture here is also very friendly nature. So, if anyone have interest, maybe they can apply for the Fondisit postdoctoral fellows. But there is also doctor fellowship, but normally I never recommend doctor fellowship, because sometimes you see most of our Indian friends, Indian students, they, the young age, they have some kind of homesick. So when they have experiences, they have little matured for postdoctoral people, maybe they can have a good time if they get the opportunity. So there are some other fellowship other countries like Mexico and Argentina, but that I only have mentioned. But because in Chile I know very well, because I was in committee expert committee for more than 5 years in the Fondisit. So if anyone interested, you can apply. Of course, it's no need to think about only stick with in India, in Tamil Nadu itself. You can go wherever. If you have good education, you can go anywhere in the world, and you can stand your own legs. Yadu Mure, Yavarum Kele. That is the short form of this both. This, I mean, this both definition. Also, you can see the Tirukkural. It means ಅದು ಮುறை ಯಾವರಂ ಕೇಳಿ. If you have good education, it's better life for anyone. Okay, thank you for the great opportunity. Thank you, Dr. Murugadas.
Thank you. Thank you
If
very
any
much, sir.
questions, I'm pleased
Thank you
to
very much for a very excellent and
respond.
informative talk.
Hello.
This is questions time. Maybe audience, you can.
Yeah, I'm Kupuswamy.
Yes, welcome, sir.
Thank you very much, Mr. Dr. Mangal. It is a very interesting, very wonderful talk. In fact, it was more educative. We seriously work on solid oxide fuel cells at Satyabama Institute of Science and Technology.
Okay.
And one of my students, Mr. Ajit Kumar, has done commendable work in this area, especially on 3 areas on electrolytes, trying to see three different approaches. One through pulse laser deposition for electrolytes, another through co-doping approach by adding sodium carbonate kind of things. And the first approach is exactly like what you have done. That is the minimum work with the GDC. And we have also gone through adding different dopants like Samaria to replace gadolinium, and also going for a strontium and kind of things. Then we have developed a half cell structure, not on a tubular configuration, but on a planar configuration. Therefore, it was a very, very interesting and wonderful coincidence of the work which what we have done it. All the work has completed, has been as coming as a journal paper in Journal of Energy and Materials Letters in the 2020. If you look at it. Hello.
Yes, I can hear you. Yeah.
Yeah.
You.
So, So I will ask my student to write to you. That is the first point.
Okay, it's a pleasure. It's my pleasure.
Yeah. And secondly, I'm very happy because I'm basically I was a metallurgist and turned to be a physical metallurgist, and I could understand that you could focus more on sintering and making a tubular configuration. That is very exciting for me, which we have not done so far. That I want to just ask you a few questions. If you are free, I will just make a question.
Yeah, it's my pleasure.
Yeah, the one thing is you made a tube which is about 5 centimeter, I think. I've noted down.
Yes.
And the diameter is about 4 millimeter. Yeah, just I want to know what is the sintered density before the tube extrusion.
Yes, the main thing is that what we focus forest tubes.
Yes.
Because we fabricate anode tubes. Anode
tubes I understand. The whole thing is fine. I just want to know the anode, what is the sintered density?
Yeah. So
you have done the extrusion. You have done the extrusion only for the anode, right?
Yes, actually, only for the anode.
I know. I got it.
So for that, we need uniform porosity. That porosity, if it is more maximum porosity, of course, it is more benefit. But at the same time, we should not lose the mechanical properties.
Exactly.
So we optimize to have a 40% porosity of the material. 40%.
Okay. And what is so sintered density could be like to 50 to 60 only then?
Yes. In that case, because concerning the mechanical properties, in that case, since maintaining the microporous and macroporous.
Okay. That means you did the extrusion immediately after the green pellet has been made, or you did a low temperature sintering for a short time, like 500, 600 degrees Celsius.
It was like a pre-sintering.
What is the typical temperature?
We done it for 1,000 degree. But
1,000 degrees. Okay.
Together with the electrolyte, we sintered at 1,200.
Okay. Because the SOC what you have developed is exactly the same thing what we did. Only thing is what we did was nickel oxide, samarium doped GDC. Then yes.
We also done it for samarium, sodium, erbium.
Yes, exactly. And the LSFC with the GDC we have done as a cathode material.
Yes.
And then I have one.
If you have students, maybe you can also ask them to focus on the reversible solid oxide fuel.
Sure. We are not started. We are not. Yes, he is now writing his thesis. After that, I will start a new program.
Yes, but I'm asking for the new students, for example.
Yeah.
New material comes. New material kind of materials. Yeah.
Okay. I will ask one more question on the flash sintering, sir. That is to create the max phases.
Yes.
Flash
sintering is not used for mass phases. It was used for the CDR-based materials.
You showed an example of GDC, correct?
Yes.
Yeah. I just want to ask you. You create a plasma and do some kind of a low voltage high current arc kind of things. What is that flash sintering? Is a plasma, you generate a plasma, or you do a spark sintering?
Yes, it's not a plasma. It's a
No, I will expand. Normally for a plasma sintering, you generate a RF plasma or a DC plasma to sinter it.
Yes.
Other approach is you create a localized arc and do a sintering, but the arc generation area will be very small.
Yes. Yes.
So the uniformity is quite less. That's why exactly I want to know flash sintering. What is the sintered density you can get? How much area you can cover?
In this case, we as I mentioned, we got nearly 98 to 99% density.
Yeah. What is the volume density you got it?
Um, uh, volume density.
What is the volume? Volume of the material, size of the material, area
Uh,
on the length.
but the size of the material was very small because as I mentioned, it is
That is
still
the
in.
point.
Yeah, you see it here, and the size, the 9 centimeter millimeter. This is
Yeah.
one,
Okay.
one
Okay.
size.
Okay. Okay. Then it is like an arc only.
Because it is like a dog for nature, because still it is in the investigation, no, but not yet commercialized well.
Yeah. No problem. No problem. I'll be in touch with you, sir. Thank you.
Yes. Okay.
Thank you. Actually, our Kupusan sir has many questions behalf of the participant, and also our next speaker is waiting. Once again, thank you very much, sir. Thank
Yeah,
you.
thank you. Murtaza, thank you so much. It's my pleasure. And if any students, if they have any doubt about the opportunities, it's not necessarily if they don't need to think about my area. If they have um, I mean, any doubts they can write, or not only to me, any other professors. They, because people, even the people, other people working here are very friendly to respond questions. So anyone can write to anyone.
Okay, thank you, sir.
Okay, thank you for the opportunity. Thank you.
Okay, thank you so much, sir. Kamalan, next speaker is waiting, the Anandaraj, Dr. Anandaraj.
Okay, see.
Thank you, sir. Thanks. I think it's midnight for you.
Yes.
Sir.
Sir, please share your screen.
Yes.
Yes.
Welcome to Dr. Anandaraj.
Yes, sir. I can hear you. You can proceed, please.
Okay, sir. Okay.
Yeah.
Could you share your PPT?
Yes, of course I can.
Okay.
Yeah, I think you people can see my slides now.
Yeah, sure.
Yeah.
Okay. I want to introduce Dr. Anandaraj Singani. Actually, Dr. Anandaraj Singani received a PhD from CSCR Sigri, Karaikudi, under the guidance of Dr. Subara Gundu on 2018. Just before his PhD defense, he was awarded the prestigious JSPS postdoctoral fellowship by the Japan Society for the Promotion of Science, Japan, where he currently works with Professor Suguru Noda and his group at Waseda University, Tokyo, Japan. During his PhD, for his achievement in electrocatalyst water spreading, he was honored with the prestigious ECS India section SK Rangarajan Graduate Student Award for the year of 2017 by the Electrochemical Society USA. As of now, he has published 58 articles in internationally reputed peer-reviewed journal with an average impact factor of 7.3. Among those 58 articles, he is the first and also corresponding author of 37 articles, and 23 of them were published in the Journal of high reputed ACS journals. His highest impact factor of the publication is 30.25. I think 25. I think it is he was published in Energy and Environmental Science. He is an associate editor of the journal Current Electrocatalyst, published by Bentham Science Publisher since March 2020. He also served as a reviewer for many journals. His research industries, materials and molecular electrochemist working actively on electroactivation of small molecules of importance in energy and environmental science and technologies. And Dr. Anandaraj?
Yes, sir. Yeah.
You can.
Thank you, Dr. Murugadas, for the very nice introduction of me. And I personally thank Dr. Murugadas, who is also a good friend and a well-wisher to me when he was in Sikri. And we spent some good time together. And I personally know him well. And I really thank the organization of Satyabhama University for arranging this talk and showing me in the limelight. Everyone needs a platform to show who they are. And as a early career researcher, I also need such opportunities. And I personally thank once again Dr. Murugadas for giving me this opportunity and share my recent works on neutral and near neutral water splitting. Electrocatalytic water splitting. So with that, I would like to proceed. As Dr. Murugadas introduced, I am currently working in Waseda University, where I just want to talk a few things about Waseda University. Waseda University is one of the best private universities in Japan and also ranked in the 180th position in World QS ranking. You can just compare it with our Indian institution, even though for a private institution, but the world ranking before 200 is very high. And there are a lot of opportunities for both doctoral courses and postdoctoral fellowships. You can approach any professor or any research group that you wish to work. And this is for the students, those who are in the research career in attending this talk. And if you have any queries about that, you can write to me personally at the end of presentation or anytime you wish to want to know something. So let me proceed. So today's talk is all about the recent advances that has recently occurred in the area of electrocatalytic materials for neutral and near neutral water splitting. So before going into specifically in neutral and near neutral water splitting, we first of all need to understand why we need water splitting and what is the milieu, the background. So we'll first skim through that one. And I asked the participants, so those who have attended my earlier talks and similar topics, please bear with me because some of the slides are going to be similar, not exactly the same. So I will be introducing the field with the same way because I cannot change it, right? So please bear with me. I will try to quick it up and so that we can enter into the contents of the today's topic. So let's see the background. So why we need water splitting at all? So I believe that most of you who are attending this talk are aware of our current energy situation because for every country in the world now for their energy need, they depend mostly on these three form of fuels, which are basically carbon, which are nothing but the coal, gas, and oil, which are predicted to be completely wiped off Earth's crust by the year 250 for oil and by the year 260 for gas and maximum by the end of this century for coal. So what will happen after this period? Because in any case, wherever we use these fossilized fuels for our combustion or energy generation, whatever the purpose, we are generating more and more amount of carbon dioxide, which are getting into the atmosphere and being preserved by the plants using photosynthesis process. But there is no way that we are getting back the fuel what we use today, because those fuels are generated because of thousands of years of actions by the geothermal reactions, which happens under the earth core, under the earth surface at high pressure and temperature. So after this century, what will we be doing for energy, for our energy needs? So this is the prime most question which has to be answered very immediately by the researchers who actively work on energy area. So that is very important. So what we can do possibly is that we can rely on alternate energy sources, okay, like renewable energies. We know our country, India particularly, which is located near to the equatorial line of Earth, have been blessed with sun throughout the year. Even for Tamil Nadu, we don't have a problem. In Tamil Nadu, we have only one season, that is summer, for all 12 months. So we are blessed with solar energy, so we can go for solar photovoltaics, so we can get energy as much as we want. But the things are totally different in countries those are located near the polar region, like Professor Mangal Raj's country, Chile. This is near South Pole, is in the southern hemisphere. They will not have enough access to solar energy throughout the year. So this means that not all renewable energies are accessible at all time for all people, those who are living in the polar region particularly. So what we have to do is we need to store this energy, whatever the renewable energy that we depend on, and those renewable energy sources are intermittent, which means they are seasonal, they are not available throughout the year. So we have to store that energy. So as far as we know, and we have developed storing mechanism in terms of batteries and supercapacitor, which are very, very incapable in my viewpoint, because if you just compare the amount of energy that we generate every day and the amount of energy that we can store in our batteries, maybe it could be lithium-ion batteries or lead-acid batteries or the supercapacitor or the combination of batteries and capacitor, which is recently called as kappa batteries. Either of them, none of them can store the amount of energy what we generate from our power plants every day, because it is not even 0.1% that we could store with the batteries that are available currently. So what we have to do is we have to go for an indirect large scale energy storage mechanism, which is nothing but hydrogen generation, which I have shown here. This hydrogen generation is actually holding a lot of promise for being the prime most and the best candidate for ensuring hydrogen economy and also ensuring sustainable future. I will explain in the later slide how it will going to help to achieve this dream of transitioning into hydrogen economy from an economy which is solely based on carbon, in which we are currently living in. So in the case of energy storage, I have now explained that batteries and supercapacitor cannot be efficient to store all the energy that we generate every day, and it cannot be used back on demand when the seasonal energies are not available for use. So the best option is hydrogen generation, in which we get electricity from renewable energy sources, and we generate electric energy. That electric energy is used to split water molecule electrochemically into hydrogen and oxygen, and we release the oxygen mostly into the environment. We don't store it usually, unless otherwise it is required for other purposes like medical assistance. So we just store the hydrogen gas. This hydrogen gas, when it is stored in an appropriate vessel, it can be used for many purposes, like again synthesizing the fuels, just using carbon dioxide, which we generate by combusting them, and we can use them to upgrade the oil products and biomass that we get in our day-to-day life, and we can use this hydrogen for producing other hydrogenated compounds of elements like nitrogen, boron, and other elements, which can give value-added products like boranes and ammonia, hydrogen, so many other things. So hydrogen is not only going to serve as a source for energy, serve as a fuel for energy generation. It is also going to be playing huge roles in all other related field. So hydrogen generation is really a topic of importance, and when we give much concerns about the current energy scenario and our almost 100% dependence on carbonaceous fuels, we must search how to generate hydrogen fuel from water in an efficient way. So that is what this whole water splitting idea is about. So that's why we need water splitting. So let me introduce water electrolysis and oxygen electrochemistry associated with this in this slide. And this animation shows you how does water electrolysis work. So in this we have two electrodes which are separated by a membrane, which is usually a proton conducting membrane. We supply water molecule on the anode compartment, where two water molecule loses 4 electron and 4 proton. These 4 electrons are actually directed in an external circuit and transferred into a cathode surface, and where the protons, which are liberated as a result of oxidation of water molecule at the anode, are conducted through the membrane to reach the cathode surface. So at the cathode surface, the electron which are directed in an external circuit are combining with the proton to form hydrogen molecule. So that's how we generate hydrogen via water electrolysis. So in this two reaction, that is proton reduction and water oxidation. Water oxidation is a multi-step process, and it can occur via any path. I have provided 4 possible paths for water oxidation, and 4 of them are resulting in 4 different products. As you can see, the 4 electron path results in oxygen molecule, and 3 electron path results in hydroperoxide radical, and 2 electron path results in hydrogen peroxide, and 1 electron path results in hydroxyl radical. So in our case, for efficient generation of hydrogen, we need this particular reaction. The first reaction, 4 electron path, is to occur in order to get hydrogen fuel in an efficient way, because this is the reaction which occurs with the low cell potential, low half cell potential. So all other reaction occurs with the high cell potential, which means that if your catalytic material that you use as an anode is not efficient in catalyzing 4-electron water oxidation, it will not actually split the water in an efficient way, so that you are going to lose more amount of energy than the amount of energy you can store as hydrogen. So this is the importance of oxygen electrochemistry in water electrolysis. So oxygen electrochemistry determines the efficiency, energy efficiency of the overall process, and also it determines the cost efficiency thereby. So because of these reasons, oxygen electrochemistry associated with water oxidation, I mean water electrolysis, is called to be the bottleneck of this hydrogen generation process via water splitting. So that is why people work mostly on this particular area of water electrolysis, I mean the anodic part, oxygen evolution reaction. In short, it is very familiarly known as OER. So yeah, in this slide, I would like to show you the difference between electrolysis and catalytic electrolysis. I used to show this particular example every time I present about water splitting, because people must understand electrolysis can be done by anything that can conduct electricity. That yes, yeah, you just just see this video. And here this guy is taking 2 stainless steel nails, and he kept it under a cup, and he's having a 9-volt battery, and he's placing those nails on the anode and cathode, and he fills it with water. So the moment he fills it with water, you can see the evolution of hydrogen and oxygen, where you see more gas, that is cathode, because that is hydrogen, and the less gas indicates the evolution of oxygen, because when you split 1 mole of water molecule, you get 2 mole of hydrogen and 0.5 mole of oxygen. So that is why you see the difference here. So this is simply nothing but the electrolysis. So okay, so this is electrolysis, but in this case he used 2 random electrodes of which property he doesn't know, of course, and he doesn't care about the amount of energy that he spent for generating that those gases, oxygen in the anode and hydrogen in the cathode, but he gets hydrogen out of it. So this particular process showed simply how hydrogen can be generated via water electrolysis. But our concept is making this particular process to be energy efficient, so that the cost of production of hydrogen by this method can be lowered down. So how can we do that? The best way to do is catalytic electrolysis. So we are going to catalyze the electrolysis process, which is otherwise known as electrocatalytic water splitting. So what we do here in catalytic electrolysis is we apply the potential or current that is exactly needed. We don't choose randomly some 9-volt battery. We don't choose some stainless steel nails randomly for electrode, and we don't do all these things. We select materials which are capable of catalyzing this off cell reaction with a minimum over potential. We select solution which are high in conductivity, so that we can avoid further energy loss, and we do everything in a systematic way. So that kind of electrolysis is called catalytic electrolysis, and we ensure high energy efficiency by interplaying with the work function and energy of interactions of the intermediates. So that's what the difference between electrolysis and catalytic electrolysis. Yes. Sorry, just a second. So now I have shown water electrolysis is a way to producing hydrogen, but we must also understand, is there any other way that could produce hydrogen more efficiently? I mean, in terms of cost efficiency, more efficiently. We have this very well-known process, which is century-old process, the steam reforming of hydrocarbons, which is done at high pressure and temperature. And this is the cheapest method for producing hydrogen gas with a purity of 99%, which is not even close to the requirement made by the hydrogen oxygen fuel cell. Those fuel cells require hydrogen gas to be present in the utmost purity, like 99.999%, because this particular method of generating hydrogen, I mean the steam reforming of hydrocarbon, they also give out some carbon monoxide and sulfur and nitrogen oxides. So those nitrogen and nitrous oxides and carbon monoxide, we know from the basic chemistry that those are strong field ligands. We know because they form pi back bonding, so that they always they always form stronger coordination bonds with metals like PT, gold, nickel, and all other metals, whichever the catalyst that you are going to use as electrode in your fuel cell. So we need hydrogen gas in the utmost purity. So This particular method, even though despite being a cost efficient method, is not a better method for producing highest pure hydrogen. So the highest purity hydrogen can only be obtained by the first method, which is nothing but water electrolysis. And we also have another related method, which is electrocatalytic water splitting, where people assist the reaction that is happening at the anode or cathode by illuminating with photon. So this is related, but this photocathode or photoanode, they suffer from corrosion when high current operations are done. So ideally, for rapid bulk amount of generation of hydrogen, you should always stick to water electrolysis. So these are the things, and these are some disadvantages of the other methods which can produce hydrogen. So this information clearly tells us that water electrolysis is clearly having several advantages, except one disadvantage, that is energy inefficiency when compared to only steam reforming of hydrocarbons. So except that, water electrolysis is the most advantageous method for hydrogen generation, because it does not require high temperature and pressure, it does not require electricity, excess intentional electricity. We can use the excess electricity from renewable energy sources, and the purity is what we need for hydrogen oxygen fuel cell. And the source and combustion product, source of hydrogen and the combustion product of hydrogen are going to be the same water molecule, which means that we will never run out of the source material for the generation of hydrogen, because beyond that we also have plenty of water in our ocean which can be split electrochemically for our hydrogen. This all indicating that hydrogen is truly going to be the future fuel, which is going to govern the whole economy, the whole global economy. And besides, this water electrolysis also do not pose other environmental threats like greenhouse gas emission, or it does not, or almost or always release any hazardous chemical. And this is the fastest method of all for generating hydrogen. And you can vary the rate of production of hydrogen just by increasing the electrode surface area. So this is overall a super method for hydrogen generation. So now let's move on to the bit of chemistry, particularly the thermodynamics of water electrolysis. In water electrolysis, we know there are two reactions occurring. One at the cathode, which is called HER, hydrogen evolution reaction, and another one at anode, which is technically called oxygen evolution reaction. So the overall free energy change that is associated with this reaction is highly positive. I mean, plus 237 kilojoule per mole, which is huge, which means that whenever we have a positive free energy change for a particular process, that process needs some amount of energy to be applied in the form of what can be done. Which means that water cannot split spontaneously into hydrogen and oxygen as per thermodynamics. So we need to supply some amount of energy. And the amount of energy I'm talking about here, is the potential that we are going to apply. Theoretically, 1.229 volt is predicted to be sufficient enough to split water molecule into hydrogen and oxygen. But the kinetic hindrances and associated entropy change, and they also contribute to the overall energy requirement, and they do not split this particular potential, do not split water at standard condition. So I mean at 25 degree 1 atmosphere pressure. So additional potential is needed, and that potential is known as thermoneutral potential. So technically there is no catalyst which can split water at 1.23 volt, and additionally 250 millivolt at least as over potential is necessary. But there are some exception for this condition where the material is extremely active or having 3D structure with a high mass loaded, highly loaded amount of catalyst, and those catalysts have delivered exceptionally well activity than where the over potential is lower than the thermoneutral over potential. So if you want to know more about the thermodynamics, you can refer my review article, this one, and let's move on to the kinetics part. So I told in water electrolysis, we have cathodic hydrogen evolution reaction and anodic oxygen evolution reaction. Cathodic hydrogen evolution reaction, this particular depiction is from Professor Cooper's book chapter, the famous book chapter in the fuel cell science, where he pictured very clearly how the energy efficiency is a critical thing in both fuel cell science and water electrolysis science. Because when we perform water electrolysis, we are losing some amount of energy here for generating hydrogen, the difference, because this is the equilibrium potential for hydrogen generation and as well as for hydrogen oxidation. And this is the equilibrium potential for water oxidation as well as for oxygen reduction. So in water electrolysis, we do this reaction in anode, water oxidation, and this reaction in cathode. In fuel cell, it comes oppositely. The hydrogen oxidation occurs at anode and oxygen reduction occurs at the cathode. In the case of hydrogen oxidation and hydrogen reduction, you can see they intersect exactly at the reversible potential where they are meant to be beginning. So there is no huge energy loss literally. So the real culprit of both fuel cell and water electrolysis is the oxygen involving anodic oxygen evolution reaction and cathodic oxygen reduction reaction. So the amount of energy you lose here is also going to contribute to the energy loss, and amount of energy you lose here during fuel cell operation is also going to contribute to the overall loss. So this is where we are losing energy, and this is where both fuel cell technology and water electrolysis technology become inefficient when compared to steam reforming of hydrocarbons. So that's why people concentrate on this particular area, how to bring this curve closer to this potential. So that's what the aim of all researchers whoever work on this particular area of research for the generation of hydrogen via water splitting. So we are going to see how this is done in neutral water splitting. So I will explain what is the difference between neutral water splitting and what are the current trends and in upcoming slides. So these are the milieu, the background. Now let's get started about the topic of the session. Yes. So water splitting can be done in extreme pH solution, also in neutral pH solution. So what are the advantages of doing water splitting in extreme pH solution is that they are almost ionic in nature. If you have pH 0, you have abundant proton, which means that you can perform hydrogen evolution reaction so easily. If you have very high pH, like extremely alkaline, when the pH is 14, you have abundant hydroxide, which means that you can easily perform water oxidation. So that is why people are sticking with either proton exchange membrane acidic water electrolyzer or anion exchange membrane alkaline water electrolyzer, which are so far the best ones for generating hydrogen from water in an energy efficient way. So because they offer low over potential, high activity, we have variety of electrocatalyst, and it also give high Faradaic efficiency, and we have high rate. The turnover frequency is very high when we do water splitting in highly acidic and highly alkaline condition. But the cons are this particular extreme pH solutions are highly corrosive, which means that we will be running out of electrode materials after some times of operation. So we need to keep on changing the electrode material after a particular period of operation. So which is not advisable in the case when the electrode material is huge in terms of expense. The cost of the material is huge. If the cost of the material is huge, and if you are needed to replace the material every while after some times of operation, and again it is going to increase the cost of production of hydrogen. So all the pros that you get with extreme pH is going to be affected by this factor. So we need to focus on the material which can do this water electrolysis operation in extreme pH with better stability. And because of its highly corrosive nature and all other solar fuel conversion devices that are practically being tested, they are not applicable. The catalyst in this condition in real solar to fuel conversion devices. Photocatalytic generation of hydrogen. Direct photocatalytic generation of hydrogen. So that's why people study neutral pH. Study water splitting in neutral pH. That can be exactly neutral. pH 7, or it could be closer to 7. And in literature, people defined it pH between 4.9 to 10.2 can be considered as neutral, near neutral solution, and the catalyst which can split water to form hydrogen and oxygen, they can be used in solar fuel conversion devices. So these are the pros with the neutral pH water splitting. And the cons are because of very low mobility of water molecule, because we always have to depend on the supporting electrolyte and the buffered anions in the solution, neutral pH solution. It delivers low activity and it always requires high over potential, which means that we are losing energy here. And it depends, the activity depends largely on the electrolyte composition. And sometimes if it is a more homogeneous catalyst, it also depends on the nature of the ligand that we use for making the catalyst. So I'll be talking about all this thing in detail in upcoming slides. So let's see the electrolytes first, because I have told that when you do water electrolysis in extreme pH solution, we have very easy option. For pH 0, you go with 0.5 molar H2SO4 or 1 molar HCl. For alkaline solution, highly alkaline solution, you go 1 molar KOH or NaOH. Very simple. So you don't have any confusion there about the electrolytes. But when it comes to neutral and near neutral water splitting, we have a variety of choices, and that has to be made depending on your the utmost end application. I mean, where you want to use your electrocatalyst eventually, and the place and the requirement. All this factor will affect the choice of electrolyte, and this is a collection of electrolyte, and you can see neutral water's pH is around 7, and we have several solutions which can have pHs closer to 7 and even below 7, and we also have a slightly moderately alkaline solution which are also considered to be near neutral waters for enabling this catalyst to be applicable in solar to fuel conversion devices. So these are the available electrolytes, and you can go for any of them depending on the eventual use of your electrocatalyst. So these are the electrolytes that we have so far, and we have encountered in literature so far for neutral and near neutral water electrolysis. So now we'll move on to the catalyst. As we say, we have a periodic table with more than 118 elements, and every year almost new elements are being made artificially, and people are keep on adding new elements into the periodic table. But among all those elements, when we talk about the neutral and near neutral water splitting, these are the 5 metals which contribute much, because in acidic and alkaline condition, ruthenium, iridium, platinum, those were actually intensively studied, but this material, no one knows the reason, but they do not perform well in the neutral condition. Fortunately, these 5 metals in the first 3D series, I mean in the 3D series, they perform relatively well for both the water oxidation and water reduction. So these are the choice of metals that we have for designing our catalyst in neutral water splitting. The main reason is that in the neutral water splitting process, these are the metal which have appropriate energy of interaction with the intermediates that are to be formed in both hydrogen and oxygen evolution reaction near neutral waters. All other metals have either form a very strong bond with oxygen, I mean metals whichever come before this, manganese. These metals form very strong bond with oxygen, so that it makes the splitting of metal oxygen bond so tedious, so that we have to apply additional energy and making it a less efficient, energy efficient catalyst. And the metals which comes after, they form metal oxygen bond very weakly, which means that the absorption free energy is very highly positive, which means the reaction not even proceed to the intermediate process. So these are the metals which have appropriate binding energy. So I mean energy of interaction of intermediates. So we have to stick with these 5 metals. So now let's move on to the homogeneous catalyst. Let me first explain what is homogeneous catalyst, and then I will move on to the topic. We know catalysis can be done in 2 ways. One is that we can fix the catalyst on a static support material, and we can let the reactant to come to the surface of the catalyst, and the reaction can be catalyzed. This is called heterogeneous catalysis. In the case of homogeneous catalysis, we have to disperse the catalyst in the same medium where the reactants are present, which means that in conventional electrocatalysis or water electrolysis, whatever I have been telling you so far, they are all done with 2 electrodes, which are actually the heterogeneous electrode surface, and those are the catalyst, electrocatalyst. And in the case of homogeneous water electrolysis, what people do is that they design an electrocatalyst which can be homogeneously dispersed into the solution, I mean the neutral waters, and you choose to inert electrodes which does not have any catalytic property for both water oxidation and water reduction, and you apply the desired potential for making the process. So this is homogeneous water splitting, and we have few interesting electrocatalysts and which I am going to talk. So among them, cobalt, nickel, and also sometimes iron, they are studied in the homogeneous form, where these metals are made as complexes of usually tetradentate or pentadentate porphyrin or phthalocyanine like macrocycles, and sometimes enzymes like microperoxidase can also be used for making these complexes, and these complexes are dispersed in waters neutrals and near neutral waters, and then potential is applied. But these catalysts have few issues which are listed here, because we know from the basic coordination chemistry that when we have hydroxide or when we have water, when we apply potential, hydroxide can be generated in situ, and those hydroxides are actually capable of hydrolyzing this particular coordination pair. So they can undergo hydrolysis and deposit as hydroxide at the bottom of the cell and lose its activity. So this is one of the major disadvantage of this particular homogeneous electrocatalyst, where the electrocatalysts are basically coordination complexes. But this problem was in recent year overcome by making ligands with a high hydrophobicity, which means that the amount of water molecule that approach or that reaches the metal center is limited, strictly limited by the hydrophobic environment of the ligand, which means that water molecule can approach the position, only the coordinating position, this position, and here in this position, and can undergo further reaction corresponding to water oxidation instead of hydrolyzing. So that's how this problem was recently overcome. Even then, it requires very high concentration of supporting electrolyte, because since the catalyst is dispersed homogeneously in water and it does not have any direct contact with the electrode, and we need supporting electrolytes to give the enough conductivity in order to ensure that the homogeneous catalysts which are dispersed in the solution are experiencing the same potential as the one which we decide to apply. So that is the reason this is facing huge difficulty. And because of very low concentration of catalyst dispersed, it also deliver low current intensity, and ligands are highly prone to chemical changes, because in water, when we apply electrochemical potential, we cannot refuse the possibility for further change in the chemistry of the ligands, which could also lead to the eventual hydrolysis of metal centers. So these are the issues with electrocatalysts. But apart from that, this is an interesting field where you see a big paper. I mean, papers in science, nature, because these catalysts are the one which offer very fundamental insights, unlike the heterogeneous catalysts. So that's why, even though it is not applicable in real cases of water splitting, I mean, for SFC devices directly for real energy efficient and other energy efficient hydrogen generation application, these offer very fundamental insights. So people are keep doing some fundamental research on this particular catalyst. And in these slides, I have shown how the effect of ligand substituents can affect the performance of an electrocatalyst. And here I have chosen this particular complex, I mean the cobalt complex, polypyridyl complex. This can be prepared in two ways, and these complexes, when these complexes, when been substituted with electron donating group, a plus I group, the ore potential is increased. When substituted with an highly electronegative group, electron withdrawing group, the ore potential is decreased. And such a relationship has never been made in heterogeneous electrocatalysis. And people did not know that by increasing the electron deficiency at the metal center with different substituents, one can increase the activity, or one can even manipulate in a way in which he wants to behave his material. So this is totally breakthrough. So a similar study was immediately published by another group, where they created another similar complex. This is the complex, and they replaced the hydrogen in this parent complex with so many other substituents. And you can see that whenever the substituent is electronegative or a minus I group, the ore potential decreases. Whenever the substituent is plus I group and electron donating, the ore potential is increasing. So the trick is you should make the metal center to crave for electrons. I mean, make it electron deficient. Then you can achieve your energy efficiency in homogeneous electrocatalysis for water splitting. So this is the recent trend in homogeneous electrocatalysis, and I will talk about the mechanism in the later part. Now let's move on to the heterogeneous electrocatalysis. So as I introduced earlier, heterogeneous electrocatalysis is where we do water splitting by fixing, or I can say by immobilizing the electrocatalytic material on a particular substrate electrode, where we apply potential directly by making electrical contact. So this is advantageous when compared to homogeneous electrocatalysis, because in the case of homogeneous electrocatalysis, we did not have direct electrical contact with the catalysts that are dispersed in solution. So we needed to depend on the large surface, a large amount of supporting electrolyte concentration. But in this case, we just avoid this difficulty. And that's why these are all able to give us very several advantages. I mean, high activity, low over potential, and long-term stability, so many other things. So let's see a few examples of such electrocatalysts that were applied recently for neutral water splitting. The very first one is the zinc cobalt hollow sphere. So this was the very recent work, and you can see just cobalt sulfide for hydrogen evolution reaction in pH7. I mean, in PBS, phosphate buffer solution, you can see the over potential is way higher. But when a simple zinc is made, added in this ratio to the parent cobalt sulfide, it delivered almost a parallel activity to that of PTC. So this was the very first time where neutral water splitting, I mean neutral water reduction for hydrogen generation can be done even without having a common ion, because before every work that have been done for neutral water oxidation have been said to have a single have been said to follow a single rule in which the catalyst must have a common anion to that of the electrolyte. So this was the first report that refused such rule. And here I have shown another example where you can see cobalt. This is actually cobalt phosphate borate complex, which was used to generate both hydrogen and oxygen. And they found that cobalt phosphate borate with this ratio delivered better HCr activity, but when the ratio is like this, it delivered better activity for OER. So just by tuning the anion and anion to metal ratio, you can also play with the activity. So you can actually make it the way in which you want to work it. So these are an example for cobalt-based heterogeneous electrocatalyst for neutral water splitting. And we also did some work on this area. This is one of our nickel-based electrocatalysts where we prepared nickel iron hydroxycarbonate, which is similar to NiFe LDH material, layered double hydroxide material. But in this case, we applied this material for neutral water splitting, where we obtained the very low. I mean, this is the lowest so far as far as neutral water splitting is concerned for 10 milliampere current density. And we also showed nickel selenide, which does not have any common ion with that of the electrolyte. I mean, the electrolyte used here is PBS, and the electrocatalyst is nickel selenide. Even then, we obtained very good activity for hydrogen evolution reaction and oxygen evolution reaction. You can see the ruthenium oxide, which is known for its very high activity for OER in acidic condition, and somehow still good activity for alkaline OER is not active in pH7. So that's why we need to search for electrocatalysts which can perform water oxidation in neutral and near neutral waters. So this is one of our results, where we found an electrocatalyst such as nickel selenide, which does not have any common ion with that of electrolyte, can also perform OER efficiently. And in heterogeneous electrocatalysis, often people make interesting findings, and this one is about change in mechanism just by the addition of base. So you can wonder how adding a base will change the mechanism, because most of the neutral water splitting studies are done in buffered solution. So when you add a small amount of base, the pH of the solution is not going to change. After all, that is the reason why we use buffer solution. So this work by this group of authors was published very recently. They proposed stepwise mechanism when they don't use any base, but when they used a base like pyridine, it assisted the deprotonation step. And this particular two-step reaction has occurred in a concerted fashion. I mean, the proton abstraction and electron release both had occurred at the same time, so that the material, catalytic material, become efficient in oxidizing water. And they also proved it by increasing the base concentration in a way by which not affecting the overall pH of the buffered solution. As you can see, when there is no base at all, very low current density and the over potential is very high. And when the base concentration is periodically increased, you can see with increasing base, it increases, the activity increases, current increases, and over potential decreases. So this clearly says that neutral water splitting is not only depending on the catalyst property, it also depends on the added materials and the electrolyte composition, and so many other things. And in a related study by another group of people, they found the pKa of added base. We know that pKa is metric used in chemical equilibria to predict the acid or base strength. The pKa of base is very important in modulating the OER activity of heterogeneous electrocatalyst. In this case, I'm showing an example of MnO2 catalyzed neutral water oxidation. In the case of MnO2 catalyzed neutral water oxidation, what happens is that the very first step is forming Mn3. I mean, this species. This is the actual species which catalyzes OER, which has to be formed from MnO2. MnO2, we know Mn is in tetravalent positive state, which has to undergo a disproportionation reaction where exactly half of the manganese is reduced to Mn2 plus state, and half of the manganese is in Mn3 plus. So the Mn2 plus, which formed as a result of disproportionation, is going to be inactive unless otherwise it is converted back to Mn3 plus species. Okay, so this can occur either this way or in a concerted pathway. So people have found that adding a base could trigger this conversion in a concerted fashion. And they also studied the pKa of the added base could also increase the activity, just like the amount of base. So when the pKa is very high, you can see very high activity and lowering in ore potential. So these are all very important findings made in this area. So I chose to share with you all. And it is the time to see the mechanisms. Because I told, because of the energy efficiency concern, OER and HR are usually done in acid and alkaline solution. And in the case of acid and alkaline solution, the general comprehension as of now for 4-electron OER is either this or this. I mean, adsorbate evolution mechanism or lattice oxygen participation mechanism. In adsorbate evolution mechanism, what happens is that oxygen, which is evolved at the end of the reaction, is not at all coming from the catalyst lattice, because we know in OER, whatever the material that you use, the real-time catalyst is always going to be the oxyhydroxide that is going to be formed electrochemically on the surface, which means that the catalyst which contains the oxyhydroxide which contains oxygen can participate in the evolved oxygen. I mean, the oxygen which is evolved because of the water oxidation reaction may also contain oxygen from the catalyst lattice. So few people believe that the lattice oxygen do not participate in the oxygen evolution reaction, and few people believe that the lattice oxygen do participate in the oxygen evolution reaction. And there are huge controversial discussion going on this area, and we don't want to divert our attention here. You just keep it in mind that an electrocatalyst can either perform oxygen evolution reaction via adsorbate evolution mechanism or by lattice oxygen participation mechanism. I'm sorry, I put the wrong abbreviation here. It should be LOM. I'm sorry. And let's move on to the mechanism of OER in neutral waters. So as I said earlier, it can either be lattice oxygen participation or adsorbate evolution mechanism. So we will not worry about that now. So this is an example of cobalt phosphate thin film catalyzed water oxidation reaction, where we have cobalt 3 and cobalt 4, which converts into cobalt 4 sites via proton coupled electron transfer reaction, where a proton and electron are concurrently removed out of the system. And when this complex is formed, and with the addition of 2 water molecules, this can evolve oxygen, forming the cobalt 2 complex. This again, on the another cycle of anodization, it will form this complex, and this process will go on. And similarly, we have nickel. Nickel also found to go such oxidation, because initially it will be in 2+ oxidation state, then it will convert into 3+ oxidation state, and it can follow any step to evolve, any of this path to evolve oxygen. And we also have manganese, which perform different path of mechanism depending on the pH at which water oxidation is carried out. So these are the mechanisms in neutral water. Let's see one by one. In the case of cobalt catalyzed proton coupled electron transfer reaction for water oxidation, and group of Nozera et al. Have done so many works on this particular material, and they initially proposed there was the formation of cobalt 4+, because cobalt 4+ is not a very common state of cobalt, oxidation state of cobalt that we encounter in our lab every day, doing everyday chemistry. It is very rare in forming forming cobalt 4 plus species in our experiment. So people initially didn't agree with them, so they went for EPR spectroscopy, where we can detect the existence of such presence of tetravalent ion. So initially what they did was at 1.3 volt, where the potential is very low, the potential where the catalyst will not undergo any oxidation, they observed only cobalt 2 plus species with the G factor value at around 5.6, which means that this species cobalt 2 plus is a high spin complex with the 4 unpaired electrons because of its D6 configuration. But when they catalyze the electrolysis with the cobalt phosphate, and when they reach the potential of 1.34, they have seen the first derivative peak for cobalt 4 plus, which has only 1 electron because it is a low spin complex, where in the T2G level we will have only 1 unpaired electron. So this gives a characteristic peak for a single unpaired electron, which is closer to the G factor of 2. So this indicated them there was formation of cobalt 4 plus. And to confirm that, they have chosen this particular cubane, where all cobalt present in them are in 4 plus state, and it also gave similar EPR spectrum. And this was their solid proof for the mechanism they proposed, and they actually confirmed it. And they also did potential dependent study for the same catalyst, cobalt pile. You can see at 1.3, you don't see any peak at around this area. 0.335 Tesla, which corresponds to the G factor of 2. And when they reach the potential of 1.4, where the oxidation of cobalt occurs, and when they reach the potential of 1.34, it even increases. So you can see the growth in peak. So amount of unpaired electron or cobalt 4 plus ion that are being formed. So this is how they actually proven this mechanism. So this shows us that mechanisms of any electrocatalyst can be revealed using very old and well-established techniques, spectroscopic techniques that we have. But recently, spectroelectrochemical techniques are gaining huge attraction, because all those experiments I have shown here, these were done with electrolytes that were frozen after the experiment. But now we can do such experiments while running the electrochemical measurement, and simultaneously we can occur EPR spectrum or any other spectroscopy that you wish to use. And in this slide, let's move on to another area of neutral water splitting. I told that unlike water splitting in acid and alkali, the water splitting activity depends largely on the pH of the solution, buffers and unbuffered solution, and also the reactant available. So here is an example of Mn2 catalyzed OER. In the first step, we see an electron injection which forms Mn3 plus, which can undergo disproportionation back to Mn4 plus and 2 plus, and this Mn2 plus have to convert it back to Mn3 plus, and this only can evolve oxygen. This happens in the pH range 4 to 8. But when pH is greater than 9 or equal to 9, this process does not happen. This disproportionation does not happen. It directly goes on to evolve oxygen. So pH matters in neutral water splitting. It doesn't depend on the electrocatalytic material you use. It is the pH which is going to determine in which way the water electrolysis is going to occur. So here we have a very systematic study by Shinagawa et al., which they reveal that the pH is very crucial in determining the activity. Here you can see this is the water oxidation activity of nickel oxide, put it on a RDE electrode, rotating disk electrode, and this is a cobalt oxide catalyst, put it on RD electrode. You can see the electrolyte solutions are different, pHs are different, and here this is unbuffered solution, and these are all buffered solution with a different pH. As you can see in high pH, 12.8, this is 0.1 molar KOH, where we don't have any issue of having sufficient number of hydroxide anion for an easy oxidation of water. So with increasing rotation per minute is not affecting the performance at all, which means that at higher pH, when the electroactive species, the hydroxide is high in abundance, its diffusion does not matter at all. But when in the case of low pH solution, where we can have two different reactants, we can have water molecule and we can also have sparely presenting hydroxide anion. So when they increased rotation speed, they observed this kind of peak, which is totally strange to observe in water oxidation reaction, because such CV or LSV is not usually seen in water oxidation and reduction reaction, because they showed that in this pH, when the solution is unbuffered, we have two different reactants, namely hydroxide and water, and hydroxide is easier to oxidize. That's why the oxidation of hydroxide occur at very low over potential. But once the hydroxide oxidation is completed, and when we reach this potential, water oxidation begins. So the nature of the solution we use, whether it is unbuffered or buffered, matters. And you can see similar trend here. To buffer the solution, the trend is similar to, almost similar to the high pH water oxidation. But when you don't buffer the solution, you will be having reactant switching. So these are the effects of BH and buffered anions and not buffering and so many other things. So I think I have taken you through very fundamentals to what is happening recently in the area. So I would like to summarize the things I have talked. And neutral water splitting is important because I have told this, increase electrocatalytic stability, eco-friendly, and it is not corrosive, and it can be applied directly to solar to fuel conversion devices. And among them, homogeneous electrocatalysis offer fundamental insights, unlike heterogeneous catalyst, and it can help us to understand how actually the metal center work in catalyzing water oxidation and water reduction. But they are not offering us high activity, lower potential, and high current density. So they are not applicable directly to the real-time SFC devices. But on the other hand, we have heterogeneous catalysts that are better because they offer better activity, better stability, and they are applicable in reality. So if you have any query related to this or overall in water splitting or any other activation of any other small molecule, electrocatalytic activation of any other small molecule, you can write to me. You are always welcome to write. And if I have said to you in some time that I will talk to you soon or I will get back to you soon, I have such a poor memory of remembering this thing. So I will always welcome you to remind me one more time. So if you have any queries or if you are up to some discussion, fruitful discussion, you can write to me either to this email or to this email.
Thank you very much, Dr. Anandaraj.
Yes. Yeah.
Really, it is a very attractive and informative talk.
Yeah. Thank you.
Thank you. Thank you. Participant, if you have any question, you can ask in the chat box. I will let you know the speaker. Otherwise, you can also contact the email ID already shown.
Yes.
Yes. Yes.
Hello.
Yes.
Sir, just out of interest,
Yes.
I'm Kuppuswamy speaking from Sadhibam Institute of Science and Technology.
Yes, sir. Yes, sir. Please.
I have been in the last couple of years listening to large amount of interest for hydrogen production.
Okay, that's good.
I know it's very important. Hydrogen is going to be the future energy, but I find less interest and less the advancements in the storage mechanisms.
Yes, exactly. That is what I have discussed in my previous talk. In hydrogen economy, we actually have three domains, sir. The first one is generation, the second one is storage, and third one is utilization. People have done many advanced work in generation as well as in utilization, but the storage, the third dimension of this hydrogen economy, is actually lacking in advancement, because hydrogen requires high pressurized vessel for storing it in the liquid medium, and people also do work on storing it as metal hydrides, which is also not a good method because it poses explosion dangers. So that is something where people need to work further to really make this dream of transitioning into hydrogen economy in the future, so that we can all grow together. It is not only in the hands of the electrochemist who generate hydrogen from water, or the electrochemist who combine the hydrogen back in the fuel cell to generate electrical energy, but the engineers who could store hydrogen in an efficient way with a low volume of vessel. It is also very important in making this dream to come true. Yes, I agree with you, sir. Yes.
Okay, thank you.
Yeah.
Another
yes,
one
sir.
Participant asked one question in the chat box.
Yeah. Yes.
With the nickel 3+ state stable in the
yes.
ligand coordination.
Yeah. You mean in the homogeneous catalysis?
Yes, maybe.
I'll go back to the, this slide is not about homogeneous catalysis. This is purely of heterogeneous catalysis, where the catalyst is a nickel borate thin film, which must not be confused with the ligand. But the homogeneous catalyst, which I showed here, I'm coming to that. Here, you can see this is a tetravalent nickel, not divalent or trivalent.
Okay.
Yeah.
And one more question. In
Yes.
terms of a coupled electron transfer with the metal ligand coordination, please explain about this one.
Coupled electron transition, proton coupled electron transfer is nothing but it just means that electron transfer and proton transfer are occurring at the same time. And sometimes this process is helped or assisted by the ligand which we have. Usually this is assisted by having a base molecule which can abstract proton out of the oxygen, which is coordinating with the metal center. And sometimes people have highly hydrophobic environment around the ligand, around the metal center, so that it can push the oxygen, which is having two non-bonding pairs of electron in their pi orbital. So the hydrophobic environment, which is rich in pi electron, when we have some aromatic rings around it, so the pi repulsion will be there, so that it assists the departure of oxygen molecule. So that's how people manipulate this proton coupled electron transfer with the help of ligands. But in my view, the ligands has nothing so much to do with the proton coupled electron transfer. It depends mostly on the metal and the energy of interaction with the metal that the intermediate has.
Okay.
Yes.
Actually, I have one doubt. Usually in electrochemistry, always telling that over potential.
Yeah.
Actually, what is the significance of the over potential?
Over potential is very important. But let me first explain what is potential, because potential is something. It's a physical measure which is usually calculated from considering the thermodynamic aspects. The free energy change. For all reaction, every reaction that are known to us are assigned to their respective potential, which are known as standard reduction potential, which are basically calculated from thermodynamic consideration. For this I showed like this. So we will consider the change in entropy, change in enthalpy, and change in free energy, and also change in other factors. So we can calculate the amount of energy, and that energy can be converted into volt. So that potential is called standard reduction potential. So if any reaction that cannot happen, or that is not happening when we apply that potential, which is defined by thermodynamics, and that reactions are said to be kinetically complex reaction, and we always have to apply some additional potential. In this case of OER and ORR, you can see 1.23 is the new reversible potential or equilibrium potential as predicted by thermodynamics, but it cannot happen at this potential because of the kinetic complexity. So we need additional potential. This much potential. Wait a second, I'll go back to the pointer so that I can easily get. So this is the point where it must occur according to thermodynamics, but it is not because of the kinetic complexity. So we have to further increase the potential at this up to this point where we see increase in current. So this difference, the actual potential at which the oxidation occurs, and the potential where it has to be occurred. So this difference is called over potential, and this determined how energy efficient is your catalyst is going to be. When you have high over potential, it means you are losing more energy and making the process cost you more. When you have low over potential, you are actually lowering the amount of energy you lose, and you are also increasing the cost efficiency. So this is the overall idea of over potential.
Okay, very good. Thank you. Thank you so
much. Thank you, sir.
One more question asked from participant. Does the catalyst activity or performance is related to the shape and the size of the nanoparticles?
Yes, of course. And not only that, and nanoparticles are excellent material. I will not disagree with that, because nanoparticles have revolutionized almost every field in the science that are known to humanity. And electrochemistry is not an exception, because nanoparticle offer high surface area, specific surface area when compared to bulk material. And whatever the activity that you see with the nanoparticle when compared to bulk is basically because of the improved surface area, not mainly, or not almost or always because of the activity improvement, because of intrinsic activity improvement. In the case of particle size dependent, yeah, I can say when you have larger particle, when you have larger particle, yeah, when you have larger particle, apparently you have lesser surface area. When you have smaller particle, for the same amount of catalyst, you have larger surface area, your activity will be higher. But recently I have done some work on differentiating the activity difference that occur because of surface area changes and because of intrinsic activity changes. And soon that work will get published, and I can share you that work in future talks. And yes, of course, by changing the particle size and the surface area and surface morphology, you can alter the activity of the catalyst.
Thank you.
Yeah.
Final question.
Yeah.
This electrochemical mechanism are reversible and surface phenomena. If it is surface phenomena, then the longevity of the catalyst is limited. Just your comment, please.
I get it. Yes, these electrochemical reactions are surface confined. There is no doubt in that one. And when you talk about water splitting specifically, they are not reversible. That is the main issue. I cannot say it is an issue. That is the main difference when compared to other electrochemical reaction. We know so many electrochemical reactions that are perfectly reversible. An example is ferroferry oxidation and reduction. And we also know so many other reactions which are quasi-reversible. And we also know some other reactions that are quasi-reversible and surface confinement, such as anodization of metal surfaces. And we have some reactions such as this one, where the product formed in the solution is keep on escaping from the solution, so that we don't have the product in the solution. It cannot be reversed back. So when it is not a reversible reaction, you don't have to worry about the surface confinement of the same. As long as your catalyst is stable, you can proceed beyond.
Okay.
No issues.
Thank
Yes.
you. Thank you very much,
Yes.
Dr. Anandaraj.
Yeah, thank you, sir.
Okay, this is the end of the session, and we requesting to participant to join in the evening session at 3:30 p.m.
Yeah.
Now this is the end of the session. Okay, thank you very much once again.
Yeah, thank you, sir.
It's a very valuable information you shared. Yeah. Thank you. Kamalan?
Will close.
So now its time is 3 o'clock, eh? 3:30, maybe.
3:30. 3:15 we will join.